Alright, this video here is just going to look at reviewing inverse functions. Really not a lot of calculus here in this video, just a quick review of inverse functions to help you out. If you recall, if we have our domain, our function certainly takes us from our domain to our range. And then of course the inverse function is going to take us back to where we started from, so to speak. So here, the range of our function is going to be the domain for the inverse function, which then means the domain of our function would be the range for our inverse function. And over here they give us the definition for our inverse function, and it tells us that if we have a function g is the inverse function of the function f, if f of g of x equals x for each x in the domain of g, and also, okay, so you got to check both of these, g of f of x equals x for each x in the domain. If that's the case, then we know that f and g are inverses of each other. So to look at an example how we can verify this algebraically, that two functions are inverses, then all we have to do is verify that f of g of x equals x, and we need to verify that g of f of x also equals x. So if we start out by looking at the two given functions here below, f of x equals 1 minus x cubed, g of x equals the cube root of 1 minus x, we can verify whether or not they are inverses. So we need to find f of g of x. So that simply means that we're going to take function g and substitute that in to function f, and therefore we will end up with 1 minus x. Well, our x is going to be the cube root of 1 minus x, and then of course all of that has to be cubed. And I think you can see what's going to happen here. Of course, the cube root and the cube is going to cancel out, so we're left with minus, and make sure you put the parentheses here, so it's 1 minus x that we're left with. And of course, if we distribute, we're going to get 1 minus 1 plus x, so we certainly end up with x. Now, does that verify that they're inverses? And hopefully you quickly say no, because we still have to check for g of f of x. So that means then that we're going to take our function f, which is 1 minus x cubed, and we have to substitute this in the place of x. So we would certainly just have the cube root of 1 minus, and put parentheses around your x here, which is 1 minus x cubed. And we certainly just simplify this, and we distribute the negative, we get 1 minus 1 plus x cubed. So the 1's cancel, and we're left with the cube root of x cubed, which certainly equals x. So now that both of these are equal to x, we can then conclude that f and g are inverses of each other. All right, the next theorem here tells us we have the existence of an inverse function, and I'm pretty sure that you've heard this statement before. Number one here says a function has an inverse function if and only if it is 1-to-1. And this is probably where you have heard of the vertical line test, or I'm sorry, not the vertical line test. Your vertical line test is a test for a function, and this would be your horizontal line test. And you recall that if you had a function and you were looking at the graph, so here we have a function maybe, and let me draw a little bit better here. Let's say we have this, and if you can draw a vertical line anywhere through here, and notice it only crosses the graph once, then we know that the function is 1-to-1, which simply means that for every x there's one and only one y value, and for every y there's one and only one x value. And if your function's 1-to-1, then it's going to have an inverse. Okay? And if and only if you're not familiar with this statement here, if and only if, that simply means we can read this statement forward and backwards. So for example, that means we can say a function, if a function has an inverse function, then it is 1 to 1. Or what the if and only if says, we can read this backward. If the function is 1 to 1, if it's 1 to 1, then it has an inverse. So you can read this either way. All right, number 2 says that if your function is strictly monotonic on its entire domain, well, then it is 1 to 1 and therefore has an inverse. Well, what does strictly monotonic mean? Well, that simply means that your graph, and we can look over here at this example, means that your graph is strictly increasing on the entire domain, which if you think about this, if your graph is constantly increasing, then it's not going to kind of double back on itself, or that means that your graph is constantly decreasing on its entire domain. So for example, if I had a graph that looked like this, clearly if we tried to do the horizontal line test, it's going to cross more than once, so therefore it's not 1 to 1, so it cannot have an inverse, and it is not monotonic because the graph is increasing, then all of a sudden it starts to decrease. And knowing that your graph decreases, well, that tells you that at some point the horizontal line test is going to fail because your graph is coming back down where you would have the same two y values. So we can look at this number 2 property by using our first derivative, because what do we know then? If we look at the first derivative, that tells us the slope. Well, if your slope is always positive for the whole function, then that means your graph is always increasing if you have a positive slope. And that's what we mean as far as this strictly monotonic. Or if you take the derivative of your function and the derivative is always negative on the entire function, then that means your graph is always decreasing because you always have a negative slope. So there's another way to look at the existence of your inverse, knowing that it's 1 to 1, and you can look at that graphically and use the horizontal line test, or we could take the derivative of the function and see if the slope is always positive or always negative. All right, next we have the reflective property of inverse functions, and this is a nice one to remember. If you notice here, we have this diagonal line y equals x, which is your identity function. So that means whatever x is, y is the same number. And if you have any function and its inverse, so here we have f of x and the inverse of f, notice that they are going to be reflected about this line y equals x. And that's going to be true for any function and its inverse. So what that really means is if our function here, x value is a, then for the inverse, the y value is going to be a. And for your function, if you have b as your y value, then for the inverse function, b is going to be an x value. So why does that work? Well, if you think about your inverse function, remember we are switching the domain and range. So what does that really mean? We're switching our x and y values. So that's why there's going to be a reflection about the line y equals x. So that kind of leads us into remembering how do we find the inverse of our function if possible. Well, we have the function f of x equals x squared, and we think about this graph. We know that the graph of x squared looks like this, so it's going to be a parabola. And we know that if we do our vertical line test, we can draw vertical lines anywhere and it's only going to cross once, so therefore we know this is a function. And if we go back and use the horizontal line test, you're like, wait a second, it doesn't pass the horizontal line test because any line we draw here is going to cross through the graph in 2 places. So therefore that tells us this function x squared is not 1 to 1. Well, if it's not 1 to 1, that means it doesn't have an inverse. Now, what's causing this to not be 1 to 1? Well, obviously, our parabola, this U-shaped, if our graph comes here and then goes back up. But is there a way that we can possibly restrict the domain? Can I restrict the domain of this function so that it would have an inverse? Well, there's a couple ways we could do this, and hopefully one way you can see is if I was to eliminate this half of the graph, and if our graph started here and just went up, then we would have a one-to-one function because it's going to pass the horizontal line test. So if we do that, we're going to restrict our domain so that our x value is what? Strictly greater than or equal to 0. So as long as x is greater than or equal to 0, so if I think of this as f of x equals x squared, and I say that our domain here, x is greater than or equal to 0, then we're going to have a function that is one-to-one. Now, if I restrict the domain and we have this new function where we have x squared and our x value is strictly greater than or equal to 0, now can we find the inverse function? Well, if we think about this reflective property, we said before that we're basically switching the domain and range, which means we're switching our x and y values. So if we want to find the inverse function, it would make sense that if f of x we know is really our y value, so we really have y equals x squared. So if we're going to look for the inverse, to me it would make sense then all we have to do is switch our x and y variables. So that's what we're going to do. Everywhere there's a y, we're going to change our y values to x, and everywhere we have an x, we're going to make that a y. So now we're on the way to find our inverse function. Once we do this step, then we simply solve for y. Well, if we want to solve for y, then we're going to end up with taking the square root. So we would have the square root of x equals y. Now, keep in mind, if we take the square root, remember this would be really plus or minus. But if you recall, if we restricted our domain before here, then that means we're going to be looking at what? We're only going to be looking at the positive, okay? And that has to do with the idea because we had restricted our domain for our function. So here we have our inverse function of f is going to be the square root of x. Now, what does the graph of this look like? Well, if you recall, and hopefully we remember this, your square root function looks like kind of half of a parabola on its side opening this way. Well, if we were to take our function here, f of x, x squared, so this here is our square root of x, and if I was taking the function, we know that we have this parabola shape here. This is our x squared. So here we have our function f and the inverse of f. And notice that they are a reflection about the line y equals x. So if you were to fold your paper on this line y equals x, these two graphs would fall right on top of each other. Okay, so that just reinforces up here this reflective property of inverse functions. So if you want to find the inverse function, you simply replace your x with your y, and then your y with your x, and then solve for y. All right, we have one more example here, and we want to find the inverse of this function. And I picked this one because for some reason this one tends to give people a little bit of a problem. And I've provided the graph of this function to the right here. We know that we have x plus 2 over x. Clearly, we have a split here at the origin because we know that x cannot be equal to 0 because that would have division by 0, which is undefined. So that's why we have a split here at 0. And we can tell that if we use the vertical line test, we would certainly have a function. It only crosses the graph at one place. And if we did the horizontal line test, we're only going to cross the function once. And be careful, a lot of people get confused right through here close to the origin. A lot of people think that this graph, as this graph comes up here, a lot of people think that this is going to cross the graph in more than one point. But you have to realize that this graph, as it comes up here, it's getting ever so close, but it's always changing just slightly. And that's the same thing over here. As the graph comes down here to the right, this line looks like a straight line, but this is where you have to realize this doesn't remain horizontal. it is slowly getting closer and closer to the x-axis. I mean, you're getting like 1/10, 1 over 100, 1 over 1,000, 1 over 10,000, 1 over a million. So it's getting extremely close. So anytime we draw a horizontal line, it's still only going to cross the graph in one place. So here, this function is going to be 1-to-1. So our first step is, we know that really f of x, that's our y value. So if we have y equals x plus 2 over x, we know that if we're going to find the inverse function, we have to replace our y with x. And everywhere there's an x, we're going to change our x variable to a y. And now we simply solve for y. And this is where you may want to pause the video and see if you can finish this problem from here. So I hope you've done that. I hope you did pause the video and try this on your own. I have a feeling some of you may have gotten stuck because there's a property here you need to remember in order to get y by itself. And let's see if you can figure it out as we go through. The first step here is we need to get y off the denominator. So we're going to multiply both sides by y, and we would get x times y equals y plus 2. And now you probably got stuck maybe because we now have xy and we have a y. So the question is, how do we get y in one single y value by itself? Well, what you need to do here is anytime you have a variable tied up into two or more pieces, two or more terms here that you can't combine together, you want to get all of those terms on one side. So I'm going to move the y over, so that becomes minus y equals 2. Now, hopefully you can look at this a minute maybe and figure out what you need to do. And if you remember factoring, we both terms have a y, so we can certainly factor a y out. And we're left with x minus 1. And that allows us to divide the x minus 1 away, so we would get y equals 2 over x minus 1. So therefore, this is the inverse function, 2 over x minus 1.